For something like 2,000 years, we saw electricity and magnetism as totally separate things, right? One was the stuff that made your hair stand on end, and the other was this weird force that made compasses point north. Two different worlds. But then, about 200 years back, a single accident, right in the middle of a lecture, changed absolutely everything. It revealed this incredibly deep connection that would reshape our world, and it all kicks off with a really simple question.
I mean, seriously, what on earth could a compass possibly have to do with a wire that's hooked up to a battery? At first glance, it seems like nothing, absolutely nothing. But as you're about to see, the answer to this question unlocks the entire field of electromagnetism.
So the story starts in 1820. You've got this Danish physicist, Hans Christian Oersted, and he's in the middle of giving a lecture. As part of his setup, he has a wire connected to a battery, and just sitting there on the table is a magnetic compass. And when he flips the switch and sends current through that wire, he notices something odd. The compass needle twitches. It actually moves. He knew right away he'd stumbled onto something huge. This was the first real proof of a link between electricity and magnetism.
So how did one little twitching needle change the world? Well, in this explainer, we're going to follow in Oersted's footsteps. We'll start with that accidental discovery. Then we'll unpack the two sides of this new force. First, how a magnetic field pushes on a moving charge, and second, how those moving charges create the field itself. From there, we'll see how we can use this to build powerful electromagnets. And finally, we'll see how this connection is so fundamental, it's used to define the very unit of current, the ampere. Oersted, of course, didn't just stop there. He dove into this phenomenon. He found that if you reverse the current, the needle deflects the other way. And the effect got stronger the closer he moved the compass to the wire. From all this, he came to a revolutionary conclusion. Moving electric charges, what we call a current, they actually produce a magnetic field in the space all around them.
And that one simple observation just kicked off a firestorm. Just a few decades later, James Maxwell managed to unify all the known laws of electricity and magnetism into one beautiful, elegant theory. And that theory led directly to the discovery of radio waves, which led to an absolute explosion of technology in the 20th century. We're talking radios, electric motors, power generators, everything. All of it built on this one fundamental link.
Okay, so Oersted showed us that moving charges are a source of magnetic fields. That's one side of the coin. But what about the other side? What happens when you already have a magnetic field and you send a charged particle flying through it? This is the second piece of the puzzle, and it's just as important.
The answer comes from something called the Lorentz force. It's basically the total force a charged particle feels from both electric and magnetic fields. And you can see right there in the equation, it combines the electric force we're all familiar with this new magnetic force. But here's the kicker. That magnetic part only shows up when the particle has a velocity, when it's moving. No movement, no magnetic force. That's the crucial bit. And this is where the magnetic force starts to get a little weird, a little counterintuitive. First, like we just said, it only acts on moving charges. A charge sitting still feels nothing from a magnetic field. Zero. Second, the force is always a sideways push. It's always perpendicular to both the direction the particle is moving and the direction of the magnetic field. And that leads to a really mind-bending consequence. A magnetic field can't do any work on a particle. It can't speed it up. It can't slow it down. It can only ever change its direction. So let's just put these two side by side to really see the difference. The electric force, it acts on any charge, moving or not. It pushes it along the field lines, and it can change the particle's energy. The magnetic force, though, totally different beast. Only acts on moving charges, pushes them sideways, and only ever changes their direction, never their energy. They're just fundamentally different ways of interacting with the world. Okay, so we've covered how a magnetic field affects a charge. Let's circle back now to Oersted's original discovery. How do we actually calculate the magnetic field that's being created by a current? To do that, we need another fundamental law of physics. And here it is, the Biot-Savart law. Now, the easiest way to think about this is that it's the magnetic version of Coulomb's law. You remember Coulomb's law for electric fields, right? Well, this law lets you calculate the magnetic field produced by one tiny little piece of a current-carrying wire. And if you add up all the little pieces, you can find the total magnetic field for any shape of wire you can imagine. And that comparison to Coulomb's law is super helpful. They're both long-range forces, for sure, but the big difference is the source. An electric field comes from a charge, which is just a number, a scalar. But a magnetic field comes from a current, and a current has a direction. It's a vector.
And that's why an electric field just points straight away from its source, while a magnetic field actually curls around its source, always perpendicular to it. Now, if you remember Gauss's law being a really nice shortcut for calculating electric fields in symmetric situations, well, Ampere's law does the exact same thing for magnetism. If you have something simple like a long, straight wire, using Ampere's law to find the magnetic field is way, way easier than trying to wrestle with the Biot-Savart law. It's just elegant. All right, we've got the theory down. We know currents make fields, and fields push on charges. So, what do we do with this knowledge? How do we actually put it to work? This is where we get to shift from pure physics to some really powerful engineering.
So let me introduce you to the solenoid. This thing is probably one of the most useful applications of this entire principle, and it's so simple. It's just a long wire that's been wound into a tight coil, like a helix. By running a current through this coil, we can generate a very specific and very useful magnetic field. So what's so special about it? Well, a long solenoid does something amazing. It creates a really strong and incredibly uniform magnetic field inside the coil, pointing straight down the middle. And outside the coil, the field is basically zero. This gives us a perfectly controlled magnetic field that we can turn on and off whenever we want. I mean, this simple device is at the heart of so much technology. It's used all the time in scientific experiments, it's in relays and valves, and it's the basis for those giant electromagnets you see in junkyards that can lift cars. It's a fundamental building block for pretty much anything that needs a controlled magnetic force. And now we've come full circle. We started this journey with an electric current creating a magnetic field. We're going to end it by seeing how the force from that magnetic field is used to define the unit of electric current itself, the ampere. The setup couldn't be simpler. You take two long parallel wires. You run a current through each one. So what happens? Well, the first wire creates a magnetic field. That magnetic field then pushes on the moving charges in the second wire. But of course, the second wire is doing the exact same thing to the first. They actually exert forces on each other. And what comes out of this is a wonderfully simple rule. If the currents are flowing in the same direction, the wires actually pull toward each other. They attract. If the currents are flowing in opposite directions, they push each other away. They repel. Which you might notice is the exact opposite of what you'd expect from electrostatics, where like charges repel. This mechanical force, this pull or push between the wires, is so precise and so fundamental that we use it to define the ampere. Instead of trying to define an amp by, say, counting the number of electrons flying by, which is basically impossible, we define it by the physical force it can create. Just think about that for a second. We are literally using magnetism to define a fundamental unit of electricity. That's how deep the connection really is. All of this led André-Marie Ampere to this one grand hypothesis, that all magnetism, everywhere, from a simple wire to a permanent bar magnet on your fridge, is ultimately caused by tiny little circulating electric currents down at the atomic level. And that leaves us with one final and really fascinating question to chew on. If Ampere was right, and all magnetism really does come from moving charges, what in the world is moving inside a simple refrigerator magnet? There's no battery, there's no wire. That question, well, it pushes us right out of classical physics and hints at a much deeper quantum property of particles like the electron. But that's a story for another time.